Hey, welcome back everybody. We're going to continue to work with switches and circuits as a representation of Boolean logic. But in this lesson, we're going to look at some more complex switch situations, which we'll call combination switches. Let's jump right in with a little review. First of all, as we saw in our last lesson, and if you haven't watched that one recently, you'll want to go back and watch our lesson on switches and circuits. But two main things I want to refresh with you. First of all, when two switches are in parallel, they complete a circuit when either one of them is closed, and that's represented by the Boolean operator of addition. And that really corresponds to an OR statement. That is to say, we'll have current flow when either A or B is closed. And that's why the Boolean operator of addition is often called the OR operator. And our other main operator in Boolean algebra is the AND operator, or the operation of multiplication, Boolean multiplication that is. This is represented perfectly by two switches that are in series because we can only have current flow if A and B are both closed. Corresponds to Boolean multiplication, that is to say the AND operator. Okay, so we looked at some simple circuits in the previous lesson. In this lesson, we want to focus on some more complex circuits. Let's draw the circuit A plus B times C and determine whether or not there's a path to complete the circuit when A is open, B is open, and C is closed. Well, in order to draw this circuit, we sort of have to respect the normal order of operations that you've learned a long time ago. Notice that parentheses are present in this circuit, and that of course gives us a priority level. That means that we should start by drawing B times C. Now, that's Boolean multiplication, and that is the AND operator, or in other words, we should draw a switch B and a switch C in series to represent that set of parentheses. Now, of course, there's more to this circuit than that. Current can flow through A or B and C. So we should have a parallel path here since we have Boolean addition, which means OR. And that parallel path will run right alongside B and C. And now we can have current flow through either one of these. And there's our visual representation. The electrons can flow through A, or they can flow through B and C. And there's our circuit. Now let's answer the second part of the question. Will we have current flow when A is open, B is open, and C is closed? That is to say, no current flow here, no current flow here, but we do have current flow here. Well, I think you can see that if A is open and B is open, then we have no path for current to flow. The fact that C is closed isn't enough to do the job, and so we can conclude that there is no current flow here. Now we can take this a step further and verify this fact with a Boolean table. And a Boolean table is almost exactly the same as a truth table. Let's take a look. Okay, you made some Boolean tables in our first lesson dealing with Boolean algebra. Let's make one for this expression, A or B times C. Well, we want to build the column for A or B times C, but we can't really do that until we have a B and C column. We have an A column, but we should build a B times C column as well. Okay, so as you saw in our first lesson on Boolean algebra, like a truth table, we want to have all the combinations of A, B, and C here. Since we have 3 switches, we'll have 2 to the 3rd possible rows, and that means we need 8 rows. And we'll have 1, 1, 1, 0, 0, 0 for the A's, 1, 1, 0, 0, 1, 1, 0, 0 for the B's, and 1, 0, 1, 0, 1, 0, 1, 0 for our C's. That's every possible switch configuration of 3 switches. So let's complete our B and C column. Do we have B and C in row 1? Yep, we do. They are both 1. B and C in row 2? No. B and C in row 3? No. No. Here we have B and C in row 5, so that's a 1. No, no, and no. Now for our last column, we're checking do we have A or B and C. So we're checking Do we have this column or do we have this column? Let's see. We know we're going to have ones in our first four rows because we have A in our first four rows. So we're going to have 1, 1, 1, 1. Row 5, do we have A or B and C? We don't have A, but we do have B and C, so that'll be a 1. Row 6, we don't have A and we don't have B and C, that's a 0. Row 7, no A, no B and C. Row 8, no A, no B and C. So there's our outcome. Now, going back to what our original question was, it was, do we have a path to complete the circuit when A is 0, B is 0, and C is 1? So what row would that be? That'd be this row right here, 0, 0, 1. And if we look at the outcome of that row, we have a 0, and that means exactly what we concluded earlier. There is no current flow here. There's 5 switch configurations that will allow current flow and 3 that won't. And A0, B0, C1 is one of the ones that won't. Okay, I'd like you to try this one for practice. Draw the circuit A or B and C or D and determine whether or not there's a path for current flow when A is closed, B is closed, C is open, and D is open. Now you might be able to answer whether or not there's current flow by just looking at that, but I'd like you to draw out that circuit. Notice that between the parentheses there's no operation there, and just like regular old arithmetic, if there's no operation shown, you can assume that that is multiplication. So pause the video, draw your circuit, answer the question about flow, and unpause to see that solution. Okay, well, here we go. And again, anything in parentheses is where we'll start drawing our circuit. So A or B in parentheses, that means that we should have an A or B path. That's the Boolean operator of addition, which means or, and so that means we should have a parallel path to start with involving A or B. Now, we should also have another path for C or D. And so we're going to have a path for C and a path for D. And those will be drawn in parallel because we can have flow through C or D. And so the key here is that our secondary operation is multiplication, that is to say, and. And so we need to put these two in series. And there's our circuit. We can flow through A or B, and we can flow through C or D. Two parallel circuits in series. Now, let's determine what our path is here. If A is closed and B is closed, that means that we do have current flow through both of those. Unfortunately, C is open and D is open, and so we have no way to get through that second part of our AND statement, and we can conclude here that there is no current flow. We won't make a Boolean table for that one, but we could. We'll keep going. Well, let's try going in the opposite direction. Let's take our circuit and write the corresponding Boolean expression. We're going to start using the term network here, and when we talk about a switch network, we're really just talking about some configuration of switches like we've been doing and like you see on your screen. So let's take a look here. We can really start anywhere we want to here, but I like to work from top to bottom. So the first thing that probably jumps out is the fact that we have a switch A and a switch B in parallel next to each other at the top of this network. So we can right away say that we have an A or B situation. Now there's certainly more to it than that, but we can put parentheses around that to show that that is one switch within this network. Now that itself is in parallel with switch B, and so we can say that our current can flow through A or B, or it can go through this bottom branch and flow through B, but it won't flow through just B, right? It'll flow through B and either A or C, and so that should be B times A or C. And there's the Boolean expression that represents this network. We've got this worked out. Now here's a second question. Can this network be simplified? And if so, how? That's where we're going to start working with these ideas in our next lesson. We're going to start applying principles of Boolean algebra to start simplifying this without having a network. But we can do it. Here's how. We're going to build a Boolean table for 3 switches, A, B, and C. And we want to build a column for our Boolean expression, A or B and A or C. Now let's work backwards to build that Boolean expression. We can't build that unless we have an A or B column. And we can't figure out this column unless we have an A or C column. But before we can build this entire expression, we're also going to need a B and A or C column. So let's fill out these columns so that we can fill out that column. Here we go. A or B. Do we have A or B? Row 1, yes. Row 2, row 3, and row 4, all those have an A. Row 5 has a B, row 6 has a B, row 7 has no A or B, and row 8 has no A or B. A or C? Yes, 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 yes. Row 5 we have C, row 6 we have neither, row 7 we have C, and row 8 we have neither. Now, do we have B and A or C? Let's take a look. We're looking at B and A or C. Here, yes, we have both. Here we have both. Here we don't have both because we're missing B. Here we have A or C but not B. Here we have both. There we don't. There we don't. And there we have neither. So now that we have this column and we have an A or B column, we can look at these two and fill out the A or B and A or C column. So do we have one or the other? Yes. Yep. Yep. Yes. 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 No. And no. So the question of can it be simplified is this column's conditions represented by another column on the table that's simpler? Well, you might notice that this column is in fact exactly the same as our A or B column. That is to say, we get all the same outcomes with a much simpler switch configuration. And so that tells us that this complicated network is really the same as just A or B. And if you go back and look at our network, you can see that if A is closed, we will have current flow. If B is closed, we'll have current flow. But for anything to flow through the bottom branch, we're going to have B closed anyway, and so that'll be satisfied by flowing through the top branch, and that means the entire bottom branch is really unnecessary. Now, there's better ways to simplify Boolean expressions than this, and that's what we're going to do in our next lesson. Okay, here's one for you for practice. I would like you to pause the video and see if you can write a Boolean expression for the network that is shown. That one's a little bit tricky, but we've done some similar. See what you can do. Unpause the video to see the solution. Okay, let's start with the top branch. You can see that we have 2 paths to get through the top branch. We can either go through switch A, or we can go through B and C. So we would start by saying that we can follow path A, or we can follow B and C in series. Now that's one path. We could put parentheses around all that. We can take a different path as well. So we could also flow through A or B in the bottom path, but if we do that, we also, that is to say times, or Boolean multiplication, we have to flow through A or C. And so a set of brackets here will really make these 2 paths pop out. There's our top branch, A or B and C together, or we can take the bottom branch, which is A or B and either A or C. Now, even though those brackets help us to really see how these circuits are designed, they're ultimately not necessary because, as you can see in our circuit, we can either flow through path A, and that'll get electron flow all the way through the circuit, or we can go through B and C, which will get us flow through the circuit, or we can take this most complicated path, which is A or B, along with, and we don't have to put the multiplication sign in there, A or C. And that's a little bit simpler representation. And I put these from top to bottom, but you could also rearrange these in other orders. So for example, you could say A or B times A or C, or B times C, or A. and those are all equivalent. Or there's several other ways you could rearrange it. I think you get the idea. As long as you have one of those, you got it. Well, situations like this are used frequently for applied logic situations. So let's suppose a new car has several safety features that will prevent the car from starting when you don't want it to. So let's suppose that the clutch, which we'll call switch C, has to be pushed in, or the transmission has to be in neutral. The passenger seat has to be empty, or the belt has to be buckled. The driver's seat belt, D, has to be buckled, and the vehicle's hood has to be closed. All those criteria have to be met for safety before the car will start. Let's suppose that each sensor is represented by a switch with the letters I've given there, and draw a network that would represent these criteria and the Boolean expression that correlates to the network. Okay, well, here we go. First of all, our first criteria is that the clutch has to be pushed in. That would be if it's a manual transmission, or if it's an automatic, it has to be in neutral. So that's an or statement, so we can either have the clutch in or the transmission in neutral. So that's the first thing that has to happen. And the passenger seat is empty or the belt is buckled. So since this is an and statement, the next thing that has to be true, it's going to be in series. And so the passenger seat has to be empty, or the belt for P, the passenger's belt, has to be buckled. We don't need both of them true, but one or the other has to be true. If it's empty, it doesn't need to be buckled, but if it's not empty, then it does have to be buckled. And the driver's seat belt has to be buckled no matter what. There's somebody driving this car, so we have to have D. And the vehicle's hood has to be closed. So no matter what, we do not want to start the car unless the hood is up, because maybe there's a technician working on it. And so there it is. There's our network. All four of these have to be met. Either the clutch is in or the transmission's in neutral, and the passenger's seat is empty or the passenger's belt is buckled, and the driver's belt is buckled, and the hood is closed. And so there's our network. Now, what would the Boolean expression be that represents this network? Well, let's start from the left. We have to have C or T. Since this is an or parallel situation, we would have to have C Boolean addition with T, C or T, multiplied by E or P. And we know that's multiplication because it's the same as a Boolean AND statement, multiplied by D, and multiplied, since it's in series, with H. And there it is. There's our Boolean expression that represents this condition. Here again, we don't need a multiplication sign between there, but you certainly could have one. There's no harm in that. I'd like you to try that same idea. A home security system will automatically dial 911 if any of the following are true. So unlike our previous example where they all had to be true, here the system will dial 911 if any of the following are true. That's going to change your approach a little bit. The smoke detector might activate and the owner is away. Well, we don't want it to activate if the owner's home because they could just be burning some food in the kitchen. Or there's motion in the house and the owner is away. We certainly wouldn't want it calling 911 if there was motion in the house while the owner was home. People could just be living their lives. Or we have an incorrect security code that's entered 3 times in a row. That's suspicious. Or there's window glass broken or a door is forced open, either during the nighttime or if the owner is away. Either of those would be suspicious. It's a little bit tricky, so treat each sensor as a switch with the letter that's given, and make a network that represents the situation, and then, like we did a minute ago, write the Boolean expression. If you can, see if you can simplify it as well. Pause the video and unpause to see that solution. Okay, well, we're going to have a little bit different approach here. This time, since any of these could be true, 4 different bullet points here, we're going to have 4 different parallel circuits, 4 different independent events that could trigger a 911 call. Let's start with the top one. The first thing that could trigger a 911 call is if the smoke detector activates, that is to say we think there's a fire, and the owner is away. Okay, so they would have to both be true in order to activate a 911 call. There's one path that could trigger a call. Another path is that there is motion in the house and the owner is away. So we could have motion and the owner being away. Our third row, we could have an incorrect security code that's entered 3 times in a row. Now, we don't need to do I, because once I is triggered, all 3 switches would close. And so we're simply saying if it is entered 3 times in a row incorrectly, that would be enough to trigger the call. And then our last one is the tricky one. Window glass is broken or a door is forced open. Now, we wouldn't want it to call during the day because it could just be a kid playing baseball that put a ball through the glass, but that will trigger a call if a window glass is broken or a door is forced open if it is either nighttime or the owner is away. If either one of those conditions are met, then it is suspicious that the window would be broken or that a door would be forced open. So that last bullet point, the window or the door will only trigger if it's either nighttime or the owner is away. So 2 of these have to be met in order to trigger a 911 call. And there's our network. 4 things that can happen in order to trigger a call. Now, what will that Boolean expression look like? Let's start from the top and work our way down. We can have F and or times A. That's one thing that would trigger a call. Or we can have M and A. That would trigger a call. Or we can have the incorrect code entered, switch I. Or we can have W or D and N or A. So there's our Boolean expression. It's kind of a big one, but there again we have 1, 2, 3, 4 different criteria that can be met to trigger a call. Now, can we simplify that? Well, take a look at this network. As it turns out, there is a little something that can be simplified. Instead of having this switch A occur in 2 different places, because the owner has to be away if there's smoke, or the owner has to be away if there's motion. Rather than having that same switch in 2 places, we could eliminate that and simply say we can have the fire detector or motion while the owner is away, and we could eliminate this whole upper switch. Which means these 2 could be simplified to say we can have F or M while the owner is away. Or we can have the incorrect code entered 3 times, or we can have W or D and nighttime or away. And that is 1 switch simpler. Now, that's not much, but it is simpler. And again, that's what we're going to focus on in our next lesson, because there's a real value in being able to take a network and write it in the most efficient way. Okay, well that wraps up this lesson. Now what we want to focus on in our next topic is learning really a new kind of algebra. You've all had some algebra before, but now we're going to use Boolean algebra to take those expressions and simplify them using a slightly different set of rules than traditional algebra does. So make sure to get help with the homework for this assignment if you need it, and we'll see you when we learn some Boolean algebra in the next lesson.